y squared equals c squared is given by the y dx equals minus x over y. So it follows then that what? Follows that the gradient of the orthogonal trajectories. Orthogonal means at right angle. All together. Orthogonal trajectories is given by m2 equal to minus 1 over m1. Is that clear? This is our own m1. Okay. So this is going to be m2 equal to minus 1 over this, our own f of x over y, that's minus x over y. That means the y dx is equal to, what will it give us? Y over x. Is that clear? Do you understand that? Y dx is equal to y over x for the orthogonal trajectory. So we can now solve this differential equation to obtain the equation defining the orthogonal trajectories. Is that clear? We're going to solve this differential equation to obtain the equation defining the orthogonal trajectories. So I believe everybody can solve this differential equation at this point. So solve the differential equation and tell me the answer. Cx.
Yes, sir.
Y is equal to Cx. Okay. Y equal to Cx. So that means that this is what? What do you call this? What's the meaning of this equation? Geometric interpretation of it. So do this before. You should be able to know what this is. Huh? What is this? What does it mean? What is this geometric interpretation or meaning? Plot the graph y equal to Cs. What's it going to give you? Huh?
It cuts across the zero.
It's a straight line.
It's a straight line.
It's a straight line because it's linear, Abi?
Yes.
Okay. And what can you say about the straight line?
It starts from x equal to slope.
Eh? That's the slope. Now the slope is given by C, Abi?
Yes.
It will have different slopes given by C. It can have any kind of slope you want it to have. And what else? It has zero intercepts on the y-axis. Can you remember that?
Yes.
Can you remember this equation of a straight line? Y is equal to mx plus c, Abi? M was what? The gradient, Abi? And c was the intercept on the y-axis. You can see that this one does not have any c. So what you have there is cs plus 0. Is that clear? That means its intercept on the y-axis is 0. Is that clear? And the gradient will be given by this c here. Is it making sense? Okay, so that means that the orthogonal trajectories, of course I told you that if you were to plot this, this is a family of circles. So with center at origin, just like I wrote here on the board, we are going to have something like this. This will be the family of circles, and then the center is at the origin. So the orthogonal trajectory to it will just be straight lines, will be passing through the origin. Any straight line passing through the origin will definitely be perpendicular to one of these circles at a particular point. Does it make sense to you at all? Alright, so that's what we mean by orthogonal trajectories. So that is that about that. So this is your answer. Just get y is equal to Cx and move on. That's the answer. Alright, so let's deal with another one. Look at number 8. Are you there? Number 8. Find the orthogonal trajectories of the family of curves cx squared plus y squared equals 1. Find the orthogonal trajectories of the family of curves cx squared plus y squared equals 1. So can you give that a try? So let's start it together. All together. Cx squared plus y squared is equal to 1. So we're going to start the same way. Cx squared plus y squared, yeah, equals 1. So we're going to start the same way. Carl. Let's ask you. Alright, so we want to see with this, we want to get its orthogonal trajectory. We are going to follow the same approach. You first differentiate it and get the expression. Now you have to hold it. Okay, so we first differentiate it and get the expression for the y dx. Well, in our expression for the y dx, we want to ensure that the constant of integration, the constant c is not there. Altogether, parameter c must not be in your differentiation when you obtain it. So you have to eliminate c. Is that clear? So let's do that now. When you differentiate this implicitly, what do you get? 2cx, Abby? Are we together? Yes. Plus 2y. Y dx equal to 0. Are we together? Yes, sir. That means the y dx is what? The y dx is equal to minus 2x all over 2y. 2 we cancel 2. That means that the y dx is equal to minus cx over y. But we will not stop here. We will have to eliminate c. So how do you eliminate c? You go to the original equation and make c the subject. So whatever you have for c there, you are going to substitute it here. Is that clear? Yes. This parameter must not be in your dy dx. So from here, we know that c will be equal to what? 1 minus y squared over x squared. So putting that here, we're going to have that the y dx is equal to minus x over y multiplied by 1 minus y squared over x squared. So we can simplify this further. I write this. You want to simplify this, how will you put that? X and x we cancel this. Does that make sense? So this is going to give us 1 minus y squared over xy. Abi? Alright. Minus 1 plus y. Right. So you have this to be y x. So that is the gradient of the family of curves. So the gradient of its orthogonal trajectory will be given by the negative inverse of this. Does that make sense? All together. This is the gradient of this family of curves. So the gradient of its orthogonal trajectories will be given by m2 is equal to minus 1 over m1. So the gradient of its orthogonal trajectories is given by the y, the x is equal to, so our dy dx will be what? The negative of the inverse of this. Does that make sense? Yes, sir. Do you understand that? Yes. Okay, this is our M1 for the given family of curves. So if you want to get the orthogonal family of curves, it's M2, okay, is going to be given by minus 1 over M1. Is that clear? I've explained this to you before that when you have orthogonal is another word for perpendicular in this case. If you have two perpendicular lines, then the gradient is related by m1, m2 is equal to minus 1. So if you want to get the gradient of one from the gradient of the other, we're going to use this expression. So it will then follow that our dy dx is equal to, what our dy dx now? To be the inverse of this, Abi, then take the negative. That means this minus will be gone, Abi. Then the inverse of it will be what? Xy over 1 minus y squared. Does it make sense? Do you understand this idea? Alright, so we now have a differential equation that defines the orthogonal family of curves. So we can solve this differential equation and get our equation for the orthogonal family of curves. Usually you will get an implicit function, and that's okay. You don't need to make y the subject here. Is that clear? Okay, so when you solve this, or how can you solve this? What kind of equation is this? What kind of equation is this? Homogeneous. Homogeneous? Who said homogeneous? Because of one, it is not homogeneous. Is it separable? Yes. So we can separate and get the answer. So I want you to solve that. Tell me your answer. What did you get?
If you talk your answer. Let's go back.
Clean 1 minus y squared. Y.
How is it close?
Okay, so what did you do? You separated the variables, right? You separated the variables, are going to have 1 minus y squared, Abi. Over y, Abi. Then the y equals to x, the x. Is that correct? Is this what you got? Yes. Then you can simplify this further and say that this is 1 over y, Abi. Then minus y. Does it make sense? Y equals to x dx. Does that make sense? Alright, so you can integrate both sides now. We're going to have this to be 1 over y dy, Abi. Then minus y squared over 2 equal to x squared over 2 plus c. So you can multiply through by 2. You multiply through by 2, what are you going to get? You can put them all together and leave the constant on the other side. We're going to have 2 in y minus y squared over 2 minus x squared over 3 equals okay, and that's okay. That what you got?
See that what you do with that? That was last so any depending on the option.
Depending on the option, yes. Alright. So let's talk about oblique trajectories. Oblique trajectories means that now you have, instead of having them at 90 degrees to each other, you have them at some angle which is not 90, maybe 45 degrees, maybe 30 degrees, maybe 60 degrees, or some undefined angle that you have to find out. Okay. So if you have a family of curves and you want to get another family of curves that is at a certain angle to them, you know what we just did now is orthogonal trajectory, meaning that you have to you were asked to find a family of curves that is perpendicular. So you may have a family of curves that is, let's say, at angle 30 degrees or some angle theta. So how do you deal with that? So in such a case, we will make use of a similar idea, but we will make use of the fact that when you have a certain angle between two lines, can you remember when you have a certain angle between two lines, you can always say that, look at this please, if you have two lines at a certain angle to each other, let's say that this line is at angle theta to this, and then this has some gradients. Okay, you want to find out the gradient of this one, M2, knowing the gradient of this one, M1. So we know that normally the gradient has to do with the angle that this thing makes with this axis. Are we together? Do you understand what I'm saying here? Yeah. So for instance, you have to do something like this and say that, let's say this thing here is at angle theta, okay, to the x-axis, and this one is at angle alpha. So if you want to get the gradient of this one, M2 is going to be equal to, you know, M1 normally is equal to tan theta. And if you want to get M2, it's going to be equal to tan theta plus alpha. So tan theta plus alpha. What do we mean by that? That means that in this case, we are interested in this angle that this makes with this axis. How did we come about this? If you look at the definition of gradient of a line, can you remember the definition for gradient of a line? Can you remember? I'm asking you now. Definition for gradient of a line. How do you get the gradient of a straight line? How do you get the gradient of a straight line? Change the y over change the x, Abi? So you're going to have something like this. If I have a line here, let's say this is some line, and I want to get the gradient, I'm going to find out the change in y over change in x. This is our change in y, and this is our change in x. Does it make sense? You know that at the same time, you can remember your SOHCAHTOA. Can you remember SOHCAHTOA? Okay. So we have change in y, okay, over change in x. Okay. You know that tan is opposite over adjacent, Abi? So if I pick some angle theta here, which is the same as this angle theta, that the line makes with the x-axis, then it will follow that my change in y over change in x, which is the gradient, is the same thing as tan theta, the tan of the angle that the line makes with the x-axis. Is it making sense?
Yes, sir.
Okay, so that means that if I have a certain line M1 that makes a certain angle theta, okay, I mean the line has magnitude M1, it makes a certain angle theta with the x-axis, then M1 is given by tan theta. If I want to get the gradient of another line that makes angle alpha with M1, then the gradient of that line will be tan of theta plus M alpha. Is that clear? When I put the two angles together, that will give me the angle that this one makes with the x-axis. Is this clear? Is this clear? Just like I have this one made angle theta with the x-axis. If I have another line here, okay, such that that line is at angle alpha to this. If I want to get the gradient of this line, so this is the line with the gradient M1, this is the line with the gradient M2. If I want to get the gradient of this line, what will it be? To be tan of alpha plus theta. Does it make sense? So if I want to get tan of alpha plus theta, what would that be? So from our trigonometry, we know what tan A plus B is. Abi? Tan A plus B is what? Tan A, tan B over 1 minus, sorry. Tan A plus tan B all over 1 minus tan A tan B. Can you remember that? Alright, so that's what we're going to use here. That this should be equal to tan theta plus tan alpha all over 1 minus tan theta tan alpha. Does it make sense? Alright, so that will give us the gradient. So that means, of course, we know that tan theta is M1, Abi? So everywhere we have tan theta, we just put M1. That means at the end of the day, okay, for that family of curves, which is an angle theta, or angle alpha, to this given family of curves, their gradient will be given by this. Tan theta is our M1 plus tan alpha, whatever alpha is the angle between them, all over 1 minus M1 tan alpha. So this will give us the gradient of that new family of curves. So instead of using M2 is equal to minus 1 over M1, which we used for orthogonal trajectories. In the case of oblique trajectories, we will use this formula to get our new gradient, okay? And then we will integrate as before. I mean, solve the differential equation as before to get the what's now oblique trajectories. Okay. I don't mind sleeping.
No sleeping.
Let me unlock. Look at number 9. Find a family of oblique trajectories. Are you there? Number 9. Find a family of oblique trajectories that intersect the family of straight lines y equal to cx at angle 45 degrees. So we have the straight line y equal to cx, and then we want to find the those trajectories that are at angle 45 degrees to our straight line. So that's going to give us what? So let's work on that together. Pay attention now, pay attention to this. Pay attention. So if we have our family of curves, y equals to cx, we want to find the oblique trajectories. We want to find out the oblique trajectories at angle alpha equals to 45 degrees. At alpha equals 45 degrees. So let's see how we go about that. The first thing is to get the gradient of this one, okay, so that we can use it to get the gradient of the oblique trajectories. Is that clear? That's the normal way we did for orthogonal trajectories. So to get the gradient of this, as usual, we're going to differentiate. Are we together, please? We're going to differentiate to obtain the y dx. So given y equals to cx, when you differentiate this, what do you get? The y dx is what? C. You know, I told you C should not remain here, Abby. So we should replace C with what? From here, C is what? Y over X. So that means that our dy dx is equal to y over x. Y dx is equal to y over x is what defines the gradient of this family of curves. Is that clear? So what's the next thing to do now? Get the gradient of the oblique trajectories. So we're going to use this formula. Is that clear? In this case, we know that our alpha is 45 degrees. Is that clear? So that means that this is our M1, and to get our M2, we say that the gradient of the oblique trajectories, the gradient of the oblique trajectories, the gradient of the oblique trajectories is given by M2 equal to that expression M1 plus tan alpha all over 1 minus M1 tan alpha. This is going to be what? Our M1 is what? Y over x. This is going to be y over x plus tan alpha. Tan alpha is what? Tan 45 divided by 1 minus M1. That's y over x is tan 45 degrees. So what's tan 45? This is going to be y over x plus 1 all over 1 minus y over x. So we're good to go, Abby. So we now have our y dx for this oblique trajectory. Is that making sense? Yes, sir. So what's the next thing to do now? To solve this, are we together? We're going to solve this for the implicit function that defines our oblique trajectories. Is that making sense? We can solve this differential equation. What kind of differential equation is this? Homogeneous. Yeah, homogeneous. Right. So you can solve for the homogeneous. You can also simplify and see if it has other forms that are simpler. But in the absence of that, I think you can just solve for the homogeneous form. If you want to simplify this, for instance, I just want to check something out. If you want to simplify this, we're going to have in the numerator x into y plus x. Does that make sense? And then you're going to have in the denominator something like x up there. So when you are multiplying this, x is going to come up here. Then you are going to have x minus y. Does that make sense? Alright, so this is going to cancel. Sorry. This is going to cancel this. Then you're going to have this thing to be y plus x all over x minus y. You understand that? You understand what I'm written? Alright, so you will be able to get this when you equate this to the y dx. So you can see that this is also an exact differential equation. You're going to have this thing to be y plus x dx. Does that make sense? Yeah. Okay, minus, that would be what? X minus y dy. Does that make sense? Am I correct? Yes. It's got to 0. Is it exact? Yes. When you differentiate this with respect to y, you get 1. With respect to x, you get minus 1. It's not exact. So it's better when you write it that way. Yeah.
I put in minus instead of plus.
What is it?
I put in minus instead of plus.
Okay. Where? Oh, you are bringing it to this side now. Sorry, minus. We are solving now as homogeneous equation. This has an homogeneous equation, so you can solve it as homogeneous equation.